Hello and welcome back to another episode of Math with Sohn. Today we are going to be doing a waves problem from May-June on an AICE exam 2020 paper 2-3. Okay, so we have two progressive sound waves, Y and Z, meeting at a fixed point P. Okay, so what that means is that we took a screenshot at point P and this was all occurring at this location type of thing. Don't get too in depth with that idea. The variation with time and displacement is shown in figure 4.1. All right. So with that in mind, we have a progressive sound wave. Progressive sound waves travel and they carry energy and momentum. Okay. Other variations of waves include a standing wave, where standing waves sometimes can carry energy, but those are normally like you got your jump rope attached to a fixed point and they created a pattern. So they're still carrying energy, but it's different because standing waves look like they're just not moving. All right. So neither of those matter, but for this problem we have state one quantity of waves Y and Z that is the same and that is different. So if we're looking at here, I'm going to start out with the different because the different clearly these do not have the same amplitude, nor does it seem like they have the same, I don't know what the right word is for it, so I would probably go with amplitude, but like this one is going up while this one is going down, so they're not in phase. But that's not a quantity, but a quantity that would be different would probably be the amplitude. All right, so the amplitude is different. Let's look at what's the same. Well, let's see what the period of each of these are. They look like they might have the same period. All right, so we got here where it goes, and it takes 3 milliseconds, it looks like. And then if we look at the other one, if we go, let's say we go from here to here, does that also look like 3 milliseconds? And I do believe it does. Look like we're in front by 1, 2, 3 tick marks, and here we're in front by 1, 2, 3 tick marks. So it's just shifted to the right by 3 tick marks, which means that they both have a period of 3 seconds. We don't need to write the 3 milliseconds, but I'm going to write it just so I don't forget it. They also look like they have the exact same frequency as well. Because if you have the same period, you're also going to have the same frequency. So period and frequency. Frequency is how many times does this occur every single second, which this would have a very high frequency. The period is very small because it's 3 milliseconds, not 3 seconds. So I think the frequency would be 1 over 3 milliseconds, which is quite a bit. All right. State and explain whether Y and Z, the waves, are coherent. Coherent, by definition, I like to think of it as the waves doing the same thing, but by definition, it's a little different than that. It means that they keep and always have the same phase difference. And if they are having the same period and frequency, then they're going to have the same phase difference. So yes, they are, because, don't abbreviate, Y and Z have / maintain the same phase difference. Okay? I didn't want to write it all out. I said it though. Determine that phase difference. Okay, so what is the phase difference? They are not off by a lot. Actually, no, they are. They are off by a lot because when this one is down, that one's up, and so on and so forth. So let's see, how could we do this? I think I'm going to look at this downward part. And I want to know how much do I have to shift this over to the left by to be able to get that. All right, there's a few different ways to do it. I'm thinking of what's the easiest. It looks like it's almost a 180-degree shift, but I don't think it's just going to be a perfect 180. So let's think this is to the right by 1, 2, I'm going to say 3. And there are 4, 5, 6, 7, 8, 9, 10. Okay, so this is 2.3 milliseconds, okay? And we need to shift it by all the way from 2.3 to 0.3. Agree with that? And if we need to shift it by that much, if we need to shift by essentially 2 seconds, if we need to go to the left by 2 seconds, not really 2 seconds, 2 microseconds, milliseconds, excuse me. If we need to shift by that out of the 3 for the period, that means that that is 2/3 of the period or 2/3 of the wave that needs to shift. Well, 2/3 of 360 would be the phase difference, and 2/3 of 360 is 240 degrees if I did my math right. All right, which is not what I would have guessed. I would have guessed closer to 180, but I guess they're a little bit more out of phase than I thought when looking here. But when I look here and here, that looks like far less. All right, so there's also another answer other than 240. If you shifted it to the right, this would be 1 second to the right. And if we shifted 1 second to the right, that would be 1/3 of 360, which is 120 degrees. Both of these should give you correct answers. All right. Visually speaking, I just thought it looked like it was half off, but which would make it 180 though. Okay. The two waves superimpose at point P. Use figure 4.1 to determine the resultant displacement at time 0.75 milliseconds. Okay, so superpose does not mean that it's going to be constructive. It could be a combination of destructive and constructive. So we need to find 0.75, which shouldn't be too hard. It looks like it is 2 and then here. So 2.5 to the left or 0.75 to the right. And at that moment, we are at, I would say, that is as close to -1 as possible. I am trying to not get meticulous with these dots. And then here we are all the way up at 4. Okay, so if this is at +4 and this is at -1, you combine the amplitudes. So the superposition would be 4 minus 1 or 4 plus -1, which is 3. Pay attention to the unit. That is micrometers, but if I look down here at my answer document, it already has the micrometers there, so I'm just going to write the 3. Okay? Moving on. The intensity of wave Y at point P is I. Determine the intensity of wave Z. Okay? So wave Y is the tall one. So wave Y is the tall one. It has an amplitude of 4. Wave Z has an amplitude of 1. Technically -1, but we're just going to say 1 there. Okay? Let's make sure. Actually, well, wait, slow down. Nope, I'm wrong. Be careful. It's not at that specific dot again. It just says the amplitude. The amplitude of wave Y is 4, but what is the amplitude of wave Z? It's at -2. Okay, so amplitude not at the specific point. Here it was at that specific point we were doing superposition. Here it's just intensity at the point that the whole graph was looking at. So I almost got it wrong. Amplitude of 2. Okay. Determine in terms of I the intensity of wave Z. So I is this one. Let's look at Y. Y, remember that amplitude and intensity have a squared relationship. Intensity is proportional to amplitude squared. So the original intensity is going to be 4 squared, which is 16. That would be wave Y. The intensity of wave Z is 2 squared, which is 4. Okay, well, what do I have to do to represent that? Okay, so it wants it, this original is what they are calling I. This is my new. What do I have to do to this original to get to the 4? Well, I would have to do 16 times 1/4 to get to 4. 4 is 1/4 of 16. So that means that we would write 1/4 of I here because that is the original wave Y that we had to deal with. It had to be in terms of Y. X Z is 1/4 of the original intensity of y. You do not want to put a sub y there, but I'm just doing that to hopefully allow you to understand a little bit better. The speed of wave z is 330 meters per second. I almost messed up again. Determine the wavelength of z. Okay, so velocity is equal to wavelength times frequency. All right. We have the velocity. And I'm kind of confused why that one. So let's see. It is a 3-pointer, so maybe there's a reason why I'm a little confused. So velocity is 330. Let's just start with that. I thought by just looking at the graph that we would be able to determine the wavelength, but that's the time. That's the period. So the period is not the wavelength, but you can use the period to get the frequency. So let's also do that. Remember that that period is equal to 1 over frequency. So we have a period of 3 milliseconds. So that would be 3 times 10 to the negative third. That was before. Remember how before I said 3 milliseconds was the period from here all the way to there. So that's going to equal 1 over frequency, or frequency is equal to 1 over 3 times 10 negative third. Okay, well this is going to be pretty easy then. We could just put in our wavelength, and we can put in our 1 over 3 times 10 negative third there. You could also figure out what that is as a decimal first, but I highly recommend showing your steps no matter what. We're going to multiply by this to get it off the bottom of the fraction, so that's going to be 330 times 3 times 10 to the negative third. That would solve for the wavelength, and I got a wavelength of 0.99 meters. And I believe that that is all she wrote. I hope I didn't make any mistakes. I did this after getting home after midnight on prom night. So until next time, stay positive, my friends, and I will see everybody later. Bye.